Hi students, in the last three videos we covered combinatorics, which happens to be one of the prerequisites for this course. In this video we get started with probability. Pretty much everyone these days familiar with concept of probability. For example, a gambler wants to know odds of winning the game before he places a bet. That means he wants to compute the probability of winning the game so that he can decide if the game is fair to bet or not. And banking software calculates the probability of loan will be repaid by looking at applicant credit history. If that probability meets certain threshold, then loan will be accepted. Otherwise, loan will be rejected. And drug companies calculate the probability of harmful side effects of the new drug they invented by looking at the data obtained by doing series of tests on people. If that probability more than some threshold, then they will not release drug into the market. Okay, pretty much all industries rely on these probability calculations. Okay, now, and we know that mathematics is logic of certainty, right? But probability is logic of uncertainty, and our life is uncertain. So we can make much better decisions in life by carrying out these probability calculations for everyday events. Now, why study probability and statistics as a computer science student? Okay, at least I can give you two important areas in computer science where the subject is used very heavily. One area is machine learning, which is a subfield of artificial intelligence. This area is about developing algorithms to make computers better at particular tasks by making it learn from examples, data, without explicitly programming the rules about the task. It is a very powerful approach. One application I can give you is spam filter. In your Gmail, there is a folder called spam, right? All the spam emails sitting in that folder. So there is a software called spam filter which classify incoming emails to two types: spam, non-spam. Non-spam emails going into inbox, spam email coming into spam folder. Okay, so what it does is it calculates the probability of that incoming email non-spam by looking at its content and from the experience of having seen a lot of examples of spam emails and non-spam emails. If that probability is more than some threshold, then that email going into inbox. Otherwise, it will be sending into spam. Okay. Another area is analysis of algorithms. Most of the time, we find worst case time complexity for given algorithm. But sometimes algorithms run very fast in practice, but when you look at worst case time complexity, it may look bad. In those times, we want to find average time complexity of an algorithm. For example, if you look at a QuickSort, it's the fastest sorting algorithm that exists, but its worst case time complexity is odd n square, while average time complexity is order n log n. But to find average time complexity of an algorithm, we should be able to deal with probability distribution of inputs we are giving. And this probability is going to be essential tool for analyzing randomized algorithms which make some random choice in some part of the logic. Okay, now let me make you feel the difference between probability problem and statistics problem. Okay, here I'm going to give you two similar examples. One example going to be probability problem, other one going to be statistics problem. The first one, example of a probability problem. Say you are about to give a test consisting of 100 GK questions, multiple choice questions, 4 options, no negative marking. And you believe that you have a zero knowledge about GK. You don't even bother to read the question. You simply pick the random option. Then what is the probability that you score at least 30? Answer will be 0.1037872. We will be able to compute it later using binomial distribution. This is a probability problem. Here we know how good you are at GK. We know something about, we know some parameter about you. Okay, that parameter represent probability you answering random question correctly. That is 1 by 4 because you simply pick the random option, right? Okay, that is 0.25. So using that knowledge, we can actually compute this probability, the probability of you scoring at least 30. Okay, example of a statistics problem. Say you attempted a test consisting of 100 GK multiple choice questions, 4 options, no negative marking, and you have some knowledge about GK. So you do read question before you pick an option and you scored 60. Then question is how good you are at GK. That means using inferential statistics one has to infer a parameter about you, say P, which represent probability of you answering random GK question correctly. Okay, so by studying your performance over these 100 questions using this data, one can infer that the P should be approximately 0.6. So in the previous problem, we know P exactly 0.25. But in this problem, we estimated P to be 0.6. So this is statistics problem. Here, we are using data to estimate some parameter. In the probability question, we know the parameter P and we are trying to answer the probability question. Okay. In the statistics problem, we are using data to estimate the parameter P, which may be used for future calculations. Okay. I hope you feel the difference between the probability problem and statistics problem. Okay. Probability theory is self-contained mathematics discipline, but statistics is built upon probability theory. In this course, first 3 units we study probability theory and last 2 units we study statistics. Okay, fine. Probability is a tool for expressing degree of confidence or doubt about some statement in the presence of incomplete information. By convention, probabilities are calibrated on the scale 0 to 1. The probability statements that we make can be based on our past experience or subject to our personal beliefs. In either case, they obey some common set of principles which can be used to treat probabilities in a mathematical framework. So, your idea is to start with few basic principles of the chance that are sufficiently simple enough so that one can feel them readily. Once these few principles are accepted, we deduce a mathematical theory which will guide us in more complicated situations. That is the game plan. Okay, probability is logic of uncertainty, right? But this uncertainty is associated with some random phenomenon. The only way to gain any information about some random phenomenon is to perform an experiment called random experiments. Now let's try to understand what do you mean by random experiment. Okay, let me define what the random experiment is here. An experiment in which the outcome of the particular performance cannot be predicted in advance with certainty. But set of all possible outcomes can be described prior to its performance. And experiment can be repeated under identical conditions. Such an experiments are called Random experiments. See, these are not like experiment you do in physics lab or chemistry lab. They are examples of deterministic experiments. In the case of deterministic experiment, if you maintain certain conditions, you can predict outcome with certainty. But in the case of random experiment, do you maintain same conditions, you cannot predict outcome with certainty. Okay? And trial. A particular performance of a random experiment is called trial. It's just a terminology that we are going to use. Okay. Now, the probability model associated with a random experiment has three main components. Sample space, which is consisting of all possible outcomes, event space, which consisting of all events of interest, and probability function, which assign number between 0 and 1 2 for each event in event space. Okay, let's talk about these components one by one. Okay, first component, sample space. For a random experiment under consideration, the set of all possible outcomes of the random experiment is called sample space, which is usually denoted by omega or capital S. Okay, and we mostly denote it by omega. Next component is event space. Collection of all events of random experiment is called event space, which is usually denoted by script F or script B. An event is a property which can be observed to hold or not to hold after experiment is done. Mathematically, event is a subset of a sample space. Okay? And next component is probability measure, or you can say probability function. For each event in event space, we associate a number between 0 and 1 called probability of an event E, and it is denoted by P of E, which measures the likelihood of event to occur. The more likely the event is, more closer to the 1 the number is. Okay? Okay, let's look at some examples of random experiments. First one, tossing a coin. When we toss a coin, we can observe two possible outcomes, head or tail. So our sample space is going to be consisting of two outcomes, H, T. H denote head, T denote tail. One typical event of interest could be landing on head, right? When you toss a coin, landing on head is going to be one typical event of interest, which is a subset of a sample space consisting of single outcome H. Okay. And next one, tossing two distinct coins. Okay. When we toss two coins, so we can observe four possible outcomes here: head, 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 tail, tail, head, tail, tail. Okay. So here the first one is result of the coin 1, second one is result of coin 2, like this. Okay. Then one typical event of interest could be getting at least one head. Okay. When we toss two coins, you may be interested in getting at least one head. Okay. So that can be described as a subset of a sample space like this: HH, HTTS. Okay, these three outcomes consisting of at least one head. Okay, so this subset represent our event of interest. Next, rolling a die. Okay, when we roll a die, we can observe number of dots on the face. Okay, so the possible outcomes are 1, 2, 3, 4, 5, 6. Okay, and one typical event of interest could be landing on a prime number. Okay, so you may see prime number of dots. Okay, like a 2, 3, 4, 5. Okay, landing on prime number. Okay, so this is how you describe sample space and typical event of interest. Next, rolling two distinct dice. Okay, in this case, we can observe 36 possible outcomes like this. Here we are collecting outcomes as order pair I comma j. Here, here I is outcome of the red die, let us say. J is outcome of white die. Okay, so I and j anything from 1 to 6. So here by product rule, the number of elements in omega are going to be 6 into 6 equal to 36. There will be 36 possible outcomes. Okay. One typical event of interest here could be sum of the dice equal to 7. Okay. So you see it consisting of 6 possible outcomes here. 1 comma 6, sum is 7, 6 comma 1, sum is 7, 2 comma 5, 5 comma 2, 4 comma 3, 3 comma 4. Okay, this is sum of the dice 7 event. Okay, so this event can be described as a subset of omega consisting of these 6 possible outcomes. Okay, next. Picking a card from well-shuffled pack of 52 cards. You should know something about cards. There will be 52 cards, 13 ranks, 4 suits. Okay, suits are 4 suits, heart card, diamond, both are red. Then clubs and spades, both are black. Okay, then ranks are 2, 3 up to 10. Then J, Q, K and A. Here A means 1 or 14, J is like 11, Q is like a 12, K is like a 13. This is the ranks 2 to 13, and A can be treated as 1 as well as 14. Okay, fine. So when you pick a card, so outcome could be any card. So there are 52 possible cards like this. Okay, you may get a 2 of spades, 2 of clubs, 2 of hearts, 2 of diamonds, like that, anything. And one typical event of interest could be getting heart card. Okay, so maybe 2 of hearts, 3 of hearts, so on, 10 of hearts, J of hearts, Q of hearts, K of hearts, A of hearts, like this. Okay, fine. Next random experiment, observing email count in a day in your Gmail account. Okay, you are observing number of emails you are getting. So that outcome could be anything from 0, 1, 2, 3, so on. There is no upper bound, so you may get any number of emails in a day. So the sample space is going to consisting of all numbers 0, 1, 2, so on. If you look at here, so far all the random experiment we got a finite sample space, but here we got infinite sample space, but countably infinite, in the sense that you can list them like first one, second one, third one, you can enumerate them. They are called countable. Here 0, 1, 2, 3, so on. They are something called countably infinite sets. Okay, here the sample space is countably infinite set, which consisting of numbers 0, 1, 2, 3, so on. One typical event of interest could be getting 100 or more mails. Getting 100 or more emails in a day. Okay, that can be expressed as a subset of omega like this, which consisting of outcome 100, 101, 102, and so on. All. Okay. Okay. Next, observing life of a new light bulb in days. See, we are observing life of a bulb. Life is a time, so which can be any real number. Unlike email count, it's not going to be whole number. It can be any real quantity. So the sample space is going to be closed interval 0 to infinity. Infinite interval starting from 0, including 0, because it may not function at all. So that's why I'm also including 0, and it may last any number of days. Okay, so that's why we have taken closed interval 0 to infinity. Now again we got infinite sample space, but this time we got interval. We cannot enumerate like earlier, so we cannot list them like 1 2 3 so on. So this set is not countable, it's an uncountable set. Okay, so this is going to be our sample space. Okay, now one typical event of interest could be the bulb lasting more than a month. Bulb lasting more than month. Okay, that can be expressed like this: open interval 30 to infinity. So I'm taking open because more than 30 days, so I'm taking open interval to infinity. Okay, this represent this event. Okay, so these are some typical examples of random experiments and corresponding sample space, and some event of interest could be like this. Okay, let us consider a random experiment of tossing a coin until we see head. Okay, in this experiment, the typical outcome look like this: tail, 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 end with a head. Okay, so our sample space will be like this. See, this is the outcome if we get head in the first trial itself, then we stop. Or in the first trial we may get tail, in the next trial we may get head. In that case, outcome is this. We may see two tails then head, or we may see three tails and we may get head on the fourth trial, like that. Okay, so we have infinitely many possible outcomes like this. Okay, so let us say ei be the event of getting head on 2i minus 1th trial for I equal to 1 2 3 so on. For I equal to 1, 2i minus 1 will be 1. That means E1 is the event getting head on the first trial. For I equal to 2i minus 1 will be 3. So E2 will be the event getting head on third trial. If I equal to 3, 2i minus 1 will be 5. So E3 will be getting head on fifth trial, and so on. Okay, fine. So then, so EI will be consisting of single outcome like this. Okay, tail, 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 head, which is a string of head and tails of length 2i minus 1, having all tails and end with a head like this. Okay, these are all tails, only head you will see at the end. Okay, the total length of the string is 2i minus 1. So EI consisting of only single outcome like this. Okay, of length 2i minus 1. Okay, fine. So how can I describe event of requiring odd number of trials to see head? Okay, so we may require any number of trials to see head, right? Now what if I am interested in requiring, what if I am interested in event of requiring odd number of trials to see head? So that can be described like this: E going to be union of I equal to 1 to infinity ei. Okay, so see, this event happening means at least one of the event happening. Okay, so E1 may happen. E1 means getting head on the first trial. E2 may happen. E2 means getting head on the third trial, or E3 may happen. In that case, getting head on the fifth trial, and so on. Okay, this is precisely the event requiring odd number of trials to see head. Okay, this E going to be event of requiring odd number of trials to see head. Okay, fine. Then what should be E complement? Then E complement denote the event of requiring even number of trials to see head. Okay, fine. Now, here, if E1, E2, so on, E1, E2, so on, En, if all are events of interest, then their union, countable union, also going to be event of interest. Okay, we call it E. If E is event of interest, then E complement also going to be event of interest. So question is, what should be our event space? Question, what should be our event space? See, in the random experiment of tossing a coin until we see head, we were interested in assigning probabilities to events and their unions and complement of events and so on. That means our event space should be rich enough to include all these combinations. So our event space should be stable with union, also countable union and complementation operations. Such a collection of events is called sigma field of subsets of omega. Okay, so let me define what is sigma field of subsets of omega. Okay, definition, sigma field. Let script f be a collection of subsets of omega. We say the script f is a sigma field on omega if it satisfies these three conditions. The first one, empty subset of omega must be candidate in the script f. So at least script f having one element which is empty subset. That's why that will make sure that script f is always non-empty. Okay, or sigma field always will be non-empty because at least empty subset of omega will be there. Next, if E is a candidate from script f, then its complement also must be candidate from the script f. Okay, that means the script f should be closed under complementation. And third, third, if E1, E2, so on, En is countable collection. Okay, if E1, E2, so on, En, all these are candidates from script f, then their countable union, union I equal to 1 to infinity Ei, also must be candidate from script f. That means the script f should be closed under countable union. Okay, if any collection of subsets of omega satisfying these three conditions is called sigma field on omega. Okay, this is the definition. So our event space should have this structure. Okay, this is the definition. Fine. Next, remark 1, the omega will be always in the sigma field. Of course, we didn't demand this thing in the definition, but they actually follow from condition 1 and 2. See, first of all, we know that the empty subset always in the sigma field by condition 1. But if empty subset is there, its complement also must be there by 2, by condition 2. But what is the complement of empty subset? All omega, right? That's why the omega will be always in the sigma field. Okay, so this is remark 1. Fine. Next, remark 2. The script f also will be closed under countable intersection. That means if this E1, E2, so on, En, if this countable collection is from script f, then their countable intersection also will be in script f. Okay, so first of all, if EIs are from script f for I equal to 1, 2, so on, then their complements also must be from script f for I equal to 1, 2, so on, because of the condition 2. Condition 2. Okay, if something is there, its complement also must be there because sigma field must be closed under complementation. Okay, fine. Now, if EI complements are coming from sigma field, then their countable union also must be from sigma field by condition 3. Now, by De Morgan laws, this is going to be equal to intersection I equal to 1 to infinity EI all complement. Okay, by by De Morgan laws. Okay, now this is a candidate from scripters. Now, again, if something from sigma field, its complement also must be from sigma field by condition 2. That's why the complement of this also must be from script f by condition 2 again. But so what is this equal to? Complement A complement all complement means A, right? You know some little, I hope you know some little set theory. So this must be equal to infinity En. So this is from script f. Okay, that's why the sigma field also closed under countable intersection. Though we didn't demand it from the definition, it actually follow from 1 to 3. Okay, countable intersection. Okay, so our event space also closed under countable intersection. Okay, fine. Okay, let me clear this. Next, remark 3. Intersection of two sigma field and omega will be again sigma field and omega. If script f1, script f2 are two sigma field and omega, then script f1 intersection script f2 also will be sigma field and omega. Okay, so we need to check three conditions for this. Okay, first of all, I want to show that empty subset always candidate from script f1 intersection script f2. But I know that empty subset is a candidate from script f1 because script f1 is a sigma field. Empty subset also candidate from script f2 because script f2 also sigma field. That implies empty subset are always candidate from script f1 intersection script f2. Okay, so the condition 1 is verified. Next, condition 2. Okay, to check condition 2, if E is a candidate from script f1 intersection script f2, then I want to show E complement also candidate from script f1 intersection script f2. Okay, so E sitting in both script f1 and script f2 means what? E belongs to script f1 as well as E belongs to script f2. Okay, now E belongs to script f1 implies E complement belongs to script f1 because of by condition 2, because script f1 is sigma field. If E belongs to script f2, E complement also belongs to script f2 because again by condition 2, because script f2 is a sigma field. Now you see that E complement belongs to script f1 as well as script f2, that implies E complement belongs to script f1 intersection script f2. Okay, second condition also verified. Now third condition, we need to verify third condition. Now if E1, E2, so on En, this countable collection, if they are sitting in both script f1 and script f2, then I want to show their countable union also sitting in script f1 intersection script f2. First of all, what is the meaning of this collection sitting in both? That means this collection in script f1 as well as script F2. But both script F1 script F2 both are sigma field. So their countable union must be in script F1. Also here also their countable union must be in also script F2. Now you see this countable union of EIs belongs to script F1 as well as script F2. That means it belongs to script F1 intersection script F2. Okay. So whenever E1, E2, so on, En, this countable collection are candidate from script F1 intersection script F2, then their countable union also belongs to script F1 intersection script F2. That implies condition 3 also verified. Okay. So intersection of two sigma field and omega will be again sigma field and omega. Not only just intersection of two, you can take any number of sigma field. If you make intersection, again you end up with sigma field. Okay, fine. Okay, remark 4. We want to show that the sigma field also closed under finite union. That means whenever E1, E2, so on, En are candidate from the sigma field, then their finite union also candidate from sigma field. It is actually a weaker condition of condition 3. So we can easily show this. What you do, simply you take En plus 1 equal to En plus 2. All these candidates you take empty subset. Okay, these are all candidates from sigma field, right? By condition 1, empty subset always candidate in the sigma field. So if I take En plus 1, En plus 2 all equal to pi, so they must be candidate from script F. Now we have E1, E2, so on, En plus 1, En plus 2, and so on. We have a countably infinite collection. These are all candidates from script F. Now, if you look at this finite union, this is same as this countably infinite union, because from n plus 1 onwards, what we have only empty subset. They will not contribute anything to union. So these two union will be same. But I can tell you this belongs to script F by condition 3 of the definition of sigma field. That's why therefore the union I equal to 1 to n ei must be from sigma field. Okay, that's why the sigma field also closed under finite unions. Okay, fine. Similarly, remark 5, sigma field also will be closed under finite intersection. That means whenever E1, E2, so on, En are coming from script F, then their finite intersection also will be in the script F. Okay, so similarly can show this. Okay, now let's look at some examples of sigma fields. The first one, script F naught, it's a collection consisting of just two sets. One is empty set, other one is whole set omega. This is going to satisfy three conditions. First, condition 1, empty set is there. Okay, then complement of empty set is going to be omega, omega complement going to be empty set. Both are sitting in script F naught, and if you take their union also will be omega. So the 1, 2, 3 conditions are fine. So this is perfectly sigma field and omega. We call it trivial sigma field. Next one, script F1, I am taking every subset of omega. Power set of omega is collection of all subset of omega, which will be again sigma field because nothing to fail. I am including every subset of omega, so we can't make any condition fail. So obviously we can easily check 1, 2, 3 conditions are fine. So this will be again sigma field on omega. Okay, it is also called trivial sigma field. So This is the notation for power set of omega, which is a collection of all subsets of omega. Okay, these two always will be sigma field on any omega. Fine. Let me give a non-trivial one. For any one subset of omega, if you include just these four subsets, empty set, E, E complement and omega, okay, this will be sigma field. You can easily check condition 1, 2, 3. Okay, you can feel free to verify this. Okay, now let me give an example of a not sigma field. Okay, examples of not sigma field. If you collect all intervals of this form of real numbers, this is not going to be sigma field on real numbers. Okay, the reason is simple. If you take the union of these two intervals of the form, here these two candidate coming from script f3, but it's not going to be sitting in script f3 because it's not even interval. Okay, simple. And next, let omega be infinite set. Let omega is infinite set, then script 4 consisting of all finite subsets of omega. Then this is not going to be sigma field on omega. Simple reason is, we know from remark 1, omega itself must be candidate in the sigma field, right? But that is not the case because omega is infinite, but script 4 consisting of only finite subsets. Okay, so omega is not candidate from script 4, so it cannot be sigma field. Okay, that's enough reason to say that this is not sigma field. Okay, now if some collection of subsets of omega that we are interested in not happens to be sigma field, then we look for smallest sigma field that contain our interested collection. Okay, that leads to the following definition. Let us say here script C is the collection of subsets of omega that we are interested in. Okay, then the sigma field generated by the script C, written as sigma of script C, this is the smallest sigma field that containing our script C. Okay, this is obtained like this. Just simply take intersection of all sigma field that contain our script C. I already told you that intersection of sigma fields again sigma field, right? So this is going to be obviously sigma field, and it's going to be non-empty intersection because at least I can see the power set of omega here. So obviously we get something here. So the smallest sigma field which contain our collection always makes sense. There will be always one. Okay. Now, now if I take omega to be real numbers and the collection of subsets are intervals of this form open, close like this, we already know from this it's not a sigma field, right? But this is going to be important collection for us in future. So we are interested in the smallest sigma field which contain this collection. Okay, so that is something called Borel sigma field. Okay, we denote it by script B. Script B is the smallest sigma field which contain this collection. Okay, so this is called Borel sigma field, and elements of this Borel sigma field are called Borel sets of R. Okay, this is going to be important sigma field for us in future. Okay, fine. Next, let me clear this. Remarks. Here, this Borel sigma field contain all singletons because any singleton can be expressed countable intersection of interval of this type. And we know that the Borel sigma field generated by intervals of these types. So these are all candidates from Borel sigma field, and sigma field also must be closed under countable intersection. That's why this intersection also must be in the Borel sigma field, so which happens to be singleton X. So any singleton subset of R is going to be Borel set. All closed intervals are Borel sets because any closed interval xy we can express like this: open closed interval xy union singleton x. And this this is the basic element in Borel sigma field because Borel sigma field generated by intervals of this type, so they are going to be candidate from Borel sigma field. And we just realized that singleton x also Borel sets, right? So, and sigma field also must be closed under finite union, so this union also must be in the Borel sigma field. That's why this closed interval must be in Borel sigma field. Okay. Next, all open intervals are Borel sets because this open interval can be expressed basic element of Borel sigma field intersection with singleton y complement. We know that singletons are elements of Borel sigma field, and singleton complement also must be there because sigma field must be closed under complementation. So we know that singletons are there. Singleton's complement also must be there in the Borel sigma field. So this is going to be element of Borel sigma field, and this is a basic element of Borel sigma field, and sigma field also must be closed under finite intersection. That's why this intersection also must be in Borel sigma field. This happens to be open interval x and y. Okay. So next, and intervals of this form closed open also must be Borel sets because they can be expressed like this: open interval xy union singleton x. We just realized that open intervals are Borel sets, singletons are also Borel set. So by finite union of Borel set should be again Borel set because sigma field should be closed under finite union. Fine. Next, intervals of this form also going to be Borel set because these intervals can be expressed like this: countable union of intervals of this form, open closed. These are basic elements of Borel sigma field. So, and sigma field must be closed under countable union. So this candidate must be Borel set. Next, and infinite intervals of this form also going to be Borel set because they can be expressed like this, and we just realized that this is a Borel set and singletons are Borel set, so closed under finite union, so this must be Borel set, which happens to be this. And similarly, intervals of this form minus infinity to x open x can be seen as complement of this interval. Okay, we already know that this closed x to infinity is Borel set, so it should be closed under complementation. So the complement of this one also must be Borel set. So this also going to be Borel set. And all intervals of this form also going to be minus infinity to closed x because they can be realized as minus infinity to x union singleton x. Okay, union of two Borel sets should be Borel sets. Fine. And all finite sets and countable subsets of R are also going to be Borel set because any finite set can be seen as finite union of singletons. Okay, that's why all finite sets are Borel sets. Any countable set can be seen as countable union of singletons. That's why any countable subset of R going to be again Borel set. Okay. So Borel sigma field contains all types of intervals and all finite subsets of R and all countable subsets of R and any subset of R that can be expressed in terms of these sets through the operations union, countable union, intersection, countable intersection and complementation operations. Okay, here is an exercise. Sigma field generated by this collection also going to be same border sigma field. Hints I gave in the notes. Okay, please try. Note, this Borel sigma field is strictly proper subset of power set of R. That means not every subset of R is a Borel set. It's hard to construct one, but they do exist. But good news is any subset of R that we can ever think of are of any practical interest included in Borel sigma field. Okay. For a random experiment under consideration, we have a sample space omega and certain subsets of omega which are events. Here we may not be interested in considering all subsets of omega as events. Okay? If script f is a sigma field of events in omega, then this ordered tuples omega comma script f is called measurable space and elements of script f are called measurable sets. Okay? If you want to develop theory of probability as a mathematical model of a chance, we need a perfect definition for the concept to start with. The definition that we are going to use consisting of three axioms that are motivated by three intuitive properties of relative frequency. Okay? First, let us look at relative frequency approach for probability. Okay, relative frequency approach for probability definition. Here we go. Suppose we repeat the experiment independently n times under identical condition and E be our event of interest. The number of times the event E happened in n trials denoted by Fn of E, which represent the frequency of event E in n trials. Then the relative frequency is going to be Fn of E by n. The number of times event happen in n trials by n. Okay, this is going to be relative frequency. So relative frequency definition of probability is given like this. The probability of event E defined as limit of the relative frequency as n go to infinity. Okay. Now what we do? Okay, now let's try to see if this definition makes sense by simulating random experiment of tossing fair coin 1000 times and let us observe the relative frequency for getting head. Okay, so what we do, we're going to plot the curve with these points n comma fn of e by n is the trial number and fn of e by n is the corresponding relative frequency for n equal to 1, 2, 3, so on up to 1000. And let's see as n increases how the relative frequency behaves. So we believe the probability of getting head should be 0.5 for fair kind. Let us see if the relative frequency curve for getting head seems to stabilize at 0.5 or not. Okay, fine. Let's look at a code. Okay, here feel free to understand this code. Okay, so here the loop run n times. Each time we flip a coin, I am observing the outcome, and if that outcome is head, then I'll increase the frequency, then I add corresponding relative frequency to the RF list and also corresponding trial numbers to X list. Then finally I will return these two lists and then I plot this relative frequency curve for getting head. Okay, let me run it. Okay, so for 0 trials there is no curve. I'm I'm going to increase the number of trials. Let us try to see how the relative frequency graph changes. 200, 300, 400, 500, 600, 700, 800, 900, 1000. See, as you see, initially there is a lot of fluctuation, but as number of trials increases, the curve seems to stabilize at see 0.497083. See this point 0.498706. See, for 1000 trials, the relative frequency curve seems to stabilize at 0.498706. If you keep on increasing the number of trials, I think it's going to approach much closer to zero point 0.5. So I think this definition seems to make sense, right? But we have some drawbacks. One drawback is actual observation of experiment may not be possible. For example, if one wants to compute the probability of atom bomb destroys particular city completely, it can't perform an experiment, right? Okay. Next, experiment may be too costly to perform, then cannot afford to repeat it large number of times. For example, if one wants to compute the probability of successful rocket launch, it's too costly experiment to repeat it, right? Okay, fine. And we don't know if the limit always exists. We feel that the relative frequency curve stabilizing, but there is no mathematical proof that that sequence always converges. But later, we will be able to show that using something called weak law of large number. In probability sense, this limit indeed exists. Okay, we don't know yet, but later we will be able to show that this relative frequency approach actually makes sense. But this definition will not be suitable for developing probability theory as the definition involves experimentation. Okay, and whenever you want to compute some probability, you have to perform experiment large number of times under identical conditions, which may not be feasible to maintain identical conditions. So there are some problems. Okay, in the next video, we are going to observe three basic properties of chance from the relative frequency definition. Then we are going to give axiomatic definition of probability using those three properties. Okay, thank you.